Today we're going to start chapter 3, which deals with exponential functions and also is going to deal with logarithmic functions, which you may remember from Algebra 2. Some vocabulary you might see today are any of these words. The ones I'm going to focus on are the natural base. That's the number e. Now I know it's the letter, but it's also a number. If you type in e to the calculator, it'll give you a value. Exponential function, exactly what that is any function that has x in the power. So like 2 to the power of x is exponential. What's not exponential is something like x to the power of 2. That's not exponential because the x is not in the power. So we need to have x in the power. All right. We'll get to some of the other words as we go along. So here are some more examples of what is exponential function, what's not. Notice x is in the power on all of these. X is the power. Here, the reasons they're not is that x is the base. That's what you would call that there. Here, there is no x. In this one, the base is 1. Base is not allowed to equal 1. So here's how these look. You have a base raised to some power is going to equal some number value. And so that's the rules, is that the power, it must be x. All right, so here's a graph. It says sketch and analyze, so I've already sketched it here. This graph describe its domain. So let's talk about domain. How far left? Well, it goes on forever to the left, so you could say from negative infinity all the way to the right, which is positive infinity, which we also know is we could rewrite that as all reals. As far as the range is concerned, it does not go down forever. This approach is an asymptote. I know this is kind of a rule breaker that usually if we have a horizontal asymptote, both ends of the graph will approach that asymptote. With exponential logarithms, that's not the case. So we're actually going to say about the range is it goes down to 0 and up to positive infinity, but it does not equal that horizontal asymptote. So that would be how you would write that. Domain, range, intercepts. There are no intercepts here. I should say no x-intercepts. The y-intercept is at 0, 1. If you look right there, we have a y-intercept at 0, 1. Unless we have a vertical stretch or a shift of some sort, it will always be at 0, 1. All right. Asymptotes, I already gave you one. This asymptote, it hits the y-axis at 0, so this would be the asymptote y equals 0. It's a horizontal asymptote. I'm just going to abbreviate that. At y equals 0. And it says, let's do our in behavior. Remember, in behavior is a limit. So we want to know what happens to y as x goes to the left, and we also are going to want to know what happens to y as x goes to the right. Well, as we go to the left, this graph approaches 0, so 0 would be the correct answer. And as we go to the right, it goes up to positive infinity. And this graph happens to increase on its domain. And its domain was all real, so increase over all reals, or you could write it this way as well. It's always increasing. All right, now let's see another one. This is a decay function. Why we call this one a decay is because it's going down from left to right. Now, a lot of these values ought to be exactly the same. So here's what I'm going to do. I'm just going to pause the video, and I'll let you try to fill in all this stuff and see if it matches up with mine. All right. Now, as I pick back up, you can see the domain is all reals, goes on forever. The range, it never crosses below 0. Remember, you go low to high. That's why it seems backwards, but you go low to high. It does not cross the x-axis, but it does have a y-intercept. Horizontal asymptote at 0 here. And also, as we want to do in behavior, as we go to the left, the graph goes up. That's what's represented right there. As we go to the right, the graph flattens out towards 0. and it's decreasing over its domain. Now, here's some for you to try.